The next talk is with Anton Dochtermann, and he is going to speak about extending and completing shellings of simplicial complexes.
Great. Thanks for the introduction. Thanks for the invitation. Yeah, it's too bad I couldn't see you guys in person, but it's nice to be back. I think I was in Sonora 2 years ago, so that was a nice visit, and yeah, hoping to make it back again soon. This talk is actually kind of an extension of what I talked about 2 years ago. I think the theme then was chordal complexes and connections to shellings, and so we'll see some of that here, but there's been some further work that I want to talk about. So a lot of this is joint work with others. I'll mention their names when we get there, and I will be speaking in English. Hopefully that's okay. Although I'll try to throw in some Spanish words here and there. I think the first and last slide has a bit of Spanish. Okay, so let me get going. Okay, so just some background definitions, probably familiar to everyone, but what is a simplicial complex? So this is a collection of subsets of a set V that's closed under taking subsets. So if I have a sigma that's an element of my simplicial complex, and I take a subset of that element, then it's also in the simplicial complex. The dimension of a simplicial complex is defined to be the largest size of a maximal element minus 1. And other terminology, so delta is pure if all those maximal elements, which are called facets, if they have the same cardinality. And again, as most people know, we want to think about simplicial complexes as topological spaces via what's called geometric realization. So I've kind of drawn a picture here of a bunch of dots. Those are the ground set, and then the subsets are indicated by here's a triangle, which is a triple, it's a subset of size 3. I'm not sure if I want to include this tetrahedron or not, but in particular, this is not a pure simplicial complex, because here's a maximal face that just has cardinality 2, and there's at least cardinality 3 maximal faces as well. So simplicial complexes, again, I probably don't have to sell this to people in the room here, but these are nice things. They allow for calculations of simplicial homology, other algebraic invariants. And what's also nice is that they can be studied with tools from commutative algebra. So people here, I'm sure, have seen Stanley Reisner rings or face rings. We'll see a little bit of that in the talk, although I'll kind of mostly avoid that. Trying to avoid most of the algebra here, but there is some commutative algebra underlying these guys. Okay, so the main definition for the talk will be the notion of a shellable complex. And so a pure, we will restrict to pure, even though it does make sense in other contexts, but for us, the complexes will always be pure. A pure simplicial complex is shellable if there exists a certain ordering of the facets. So I'll call it F1 through Fs, and the condition is that whenever I take, so this is the notation for taking the union of the first, k minus 1 facets, and then this bracket means take the simplicial complex generated by it. I intersect that with the simplicial complex generated by a facet. That should be pure of codimension 1, so of dimension d minus 1. I think a picture kind of explains this if you haven't seen it before. So here's an example of a shellable complex with a Schelling order. So here's F1. And the idea now is I have to add these faces, these facets, so that they intersect in a one-dimensional pure simplicial complex. So F2 gets added, F3 gets added. Every time I add it, I intersect in a one-dimensional thing. I can actually add another one here, right? And that would intersect in a one-dimensional thing. So here's an example or a non-example, right? So, I mean, I claim that there exists no ordering of the facets where this is this is actually not a simplicial complex, because you have this kind of double edge here, but this is a CW complex. It's not shellable, and maybe take my word for it that there's no way to order these facets with this nice intersection condition. Actually, we'll see in a second why I can tell this is not shellable, but that's the idea. It's kind of like how you would peel an orange, or maybe reverse peel an orange. You want to put these facets in so that they intersect the previous things in a nice codimension 1 complex. Okay, so who cares about shellable complexes? Well, lots of people do, I guess, is one answer. But so some examples of some applications is that it controls the topology of the simplicial complex. It turns out that shellable complexes always are homotopy equivalent to wedges of spheres or contractible, like in that example before. And on the algebraic side, it turns out that if delta is shellable, then its Stanley-Riese ring, this thing I mentioned, is what's called Cohen-Macaulay, which has some nice applications to upper bound theorems and other kind of big theorems and face counting, things like that. And they also, these shellable complexes show up in the wild, right? So shellable complexes include boundaries of simplicial polytopes. So it turns out if you have a polytope where the boundary is a simplicial complex, then like an octahedron, right? These are always shellable simplicial complexes. And in fact, you can describe the shellings in a nice way. There's a kind of a family of canonical ways to shell them. Independence complexes of matroids are shellable as well. I'll say a little bit about matroids later. And then shellability also kind of restricts the skeleta. So if you have a shellable complex, then any skeleton, so that the faces up to dimension k, say, will be a shellable complex of dimension k. And in particular, one that I just want to point out, because we're going to talk about it later, is I'm going to use this notation delta sub n-1 to the k. That'll be the k skeleton of a simplex on, say, 1 through n, right? So it's an n-1 dimensional simplex. You take all the faces up to dimension k, and that's a shellable complex. So shellability is nice, but it's actually hard to tell, which is probably not surprising, but only recently this team of, I guess, 5 authors proved that it's in fact NP complete to, if you give me a d-dimensional complex on n facets, that's an NP complete question in n, right? So it's hard. And so, that might sort of motivate, is there some class of complexes where a greedy algorithm might work for a shelling, right? Is there a way to just sort of shell, whenever I can, and then kind of get to the complex that I want? So that motivates this definition that we'll say a shellable complex is extendably shellable if any shelling of a subcomplex can be extended to a shelling of delta. So what I mean by a subcomplex here is just a collection, a subset of the facets. You've given me a shellable complex delta, and I can say, well, if you shell basically if you start the shelling in a certain way, can I always finish it to a shelling of delta? And so much less is known about extendably shellable complexes, I would say. It turns out that any 2-dimensional triangulated sphere, which is necessarily polytopal, is extendably shellable. A nice result is that all rank 3 matroids are extendably shellable. The independence complexes are extendably shellable. We knew they were shellable. It turns out that not all matroids are extendably shellable, but all rank 3 matroids are. On the other side of kind of small codimension, any D sphere with D plus 3 vertices is extendably shellable. On the other hand, there's some I would say nice complexes that are shellable, but are not extendably shellable. And Siegler has shown that there's some simplicial 3 spheres with this property. So it's kind of a mysterious class of complexes, I would say. And in particular, there's this conjecture by Simon that says that the K skeleton of a simplex is extendably shellable. So this is our notation of the K skeleton of a simplex on 1 through n, right? We know that's a shellable complex. The question is, can you greedily shell it? Can you just sort of throw in these facets whenever you can, and then end up with the shelling of the entire skeleton? So some known cases, I should say that k equals 0, k equals 1 is trivial. K equals 2 is actually a special case of that Bjorner, Bjorner-Eriksson result, because, right, remember the 2 skeleton of a simplex is a special kind of rank 3 matroid. It's a uniform matroid. So that follows from their result. More recently, this team of authors proved the case for k, bigger than n-3, bigger than equal to n-3. And we also, I'll kind of show you a proof of this, of the same statement using chordal graphs. I should say questions are allowed, of course. I can't see the chat right now, but if people have questions, let me know. Changing gears a bit. So what do I mean by chordal graph? So a chordal graph is a graph that has chords, so meaning it has no induced cycles of length 4 or more. So in this column, you see that every induced, well, every cycle that you see has a chord, if it's length 4 or more. On the other hand, in this column, right, you see that this guy has an induced 4 cycle and it has no chord. This is not chordal. So all induced cycles should be length 3 or smaller. I guess just length 3 if they're simple. And chordal graphs are themselves an important object in combinatorics and other fields. What makes them so nice, I would say, is that there's various ways to characterize them. They can be characterized in terms of what are called perfect elimination orders, minimal separators. And there's even a commutative algebraic characterization that says that the complement of a graph is chordal if and only if this, what's called the edge ideal, has a linear resolution. So I'm not going to say much about that, but just this is kind of how I got into this, actually. So it may be nice to know that there's some connection there. Now, I guess sort of 4 years ago now, there was another characterization of chordal graphs that had kind of a different flavor. It seemed to be new. As far as I know, it's new. And what these Culbertson, Guralnick, Stiller say that a graph G is chordal if and only if I can obtain it from a complete graph. So complete graph, right, means it's a graph with all possible edges. And I have a rule for deleting what are called exposed edges. So maybe okay, so an exposed edge, an edge is exposed if it's contained in a unique maximal clique. Okay, so a maximal clique is it's a complete subgraph, and it should be, the edge should be contained in one and only one of those. So let me give an example here. I start with a complete graph on 5 vertices, and let's see, it looks like I removed 1, 3, the edge 1, 3, which is of course in a unique maximal clique, because when I start, there's just the one clique, right? It's a complete graph to begin with. But now here, right, I have some choices. So looks like I've removed 1, 4 because that's in the clique 1, 2, 4, 5, right? And that's the unique maximal clique that it lies in. And now I've removed 1, 5 because that's in the 1, 2, 5, right? And etc. So maybe just to emphasize, like 4, 5 in this picture is, hopefully this is clear, right? 4, 5 is in the triangle 2, 4, 5 and 3, 4, 5. So this 4, 5 is an example of something that's not exposed. It's in 2 different maximal cliques. Okay, so the theorem says that it's chordal if and only if you can obtain it this way. And again, it's kind of different flavor from other characterizations, and it has the flavor of this sort of free faces from simple homotopy theory. We'll say a little bit more about that later. Okay, so that's a nice characterization of chordal graphs. What does that have to do with kind of shellings? Well, so 3 years ago now, I guess, I kind of noticed that there's this connection to Shellings. So let me just set some notation here. If you have a graph on vertex set 1 through n, let me take a complex whose facets are just the complements of those edges. Okay, so I'll show you a picture down here, but the result, the observation is that when you take an edge in a chordal graph and you want to know, is it exposed? That's if and only if the complement of that edge is a Schelling move for this complement complex. Okay, so that's a lot of words. Maybe let me show you with an example. So on the bottom here, I have right, these graphs with exposed edges being removed. And what I've drawn up here is the complement of the edge that I've removed, right? So in the beginning, I have nothing. I removed 1, 3, and that's the same as putting down 2, 4, 5, right? So of course, that's a Schelling move because it's the first facet. And then now when I remove 1, 3, that's the same as, 1, 4. Did I do this right? Yeah, 1, 4, right? That's the same as adding 2, 3, 5. And that's a Schelling move, right? So F2 intersects F1 in an edge, okay? And etc. So every time I remove an exposed edge here, it's a facet that I'm adding that is a Schelling of the corresponding complex. So I don't know, I guess I'm saying here that if I remove 2, 4, that would correspond to adding 1, 3, 5, which would be another Schelling move that I could perform here. And just to give you a kind of, if you're familiar with the sort of Stanley Reasoner theory, there is a kind of monomial ideal underlying all this. And it turns out that, when I'm adding the corresponding generator, what I get is this nice colon ideal. This is what's called a linear quotient. And this is kind of like the perspective I took on this, but it's not so important here. But if you think about these things, this is kind of what's happening on the algebraic side. And I want to mention that just this notion of exposed edges, right, it's easy to generalize. I mean, I'm not going to go through the details here, but this idea of taking away exposed edges also works for hypergraphs, or I'll call them clutters. Or but just to give you kind of a quick maybe example here, if you take all three subsets of 1, 2, 3, 4, 5, right, you can do the same thing removing triangles. So before we were removing edges to get a chordal graph, you can now remove these triangles or three subsets. And so if you start with all three subsets of 1 through 5, you remove 1, 2, 5, which is uniquely contained in this clique. 1, 3, 5 is uniquely contained in this clique. 1, 4, 5, which is itself a clique, that's allowed. What you get is a complex that looks like this. Well, I should say that the middle triangle is there. 2, 3, 4 is still there. And so this is kind of like a chordal complex, because if you think of that bipyramid as bounding a homology cycle, then it actually has a chord, right? The triangle there is the triangle on the cutting it in half. That's kind of playing the role of a chord in a usual cycle, and so this is kind of what the complexes you get from this construction look like. I want to call these guys quotient chordal complexes. And it's also true, this statement that I have here, this proposition holds true that when you remove these exposed circuits, they are the same as shellings of these complement complexes. And so it gives you kind of a new way to think about Simon's conjecture. Okay, but going back to graphs, what we could prove here is that, so going back to graphs and Simon's conjecture, with Culbertson, Guralnick, Stiller, we could show that, in fact, any shellable n-3 dimensional complex with n vertices is extendably shellable. So, forget about the, skeleton of a simplex. Now, this is actually just any complex that has sort of not many vertices, right? So you're n-3 dimensional on n vertices. And we just use this result that I just mentioned, that shellings of such complexes are really about chordal graphs. And so the proof here is just quote unquote just graph theory. What we actually could prove is that if you take any chordal subgraph H of a chordal graph, then you can obtain H by a sequence of removing exposed edges. So you start with any chordal graph, any chordal subgraph, and you can get to that subgraph by just removing exposed edges. And so this is a generalization of these results. I mentioned the Kleinschmidt result that says spheres with few vertices were extendably shellable. And it's also, right, it's much stronger than the n-3 case of Simon's conjecture. It's also tight. I mean, you could say, well, how close are we to these two concepts coinciding? But actually, there are two-dimensional complexes on 6 vertices that are shellable but not extendably shellable. Okay, so I want to anyway. So that's the kind of first result there. I want to change gears. I want to change perspective a little bit now, and kind of forgot when I should stop, but maybe I'm not there yet. Hopefully, so I want to change perspective on Simon's conjecture a little bit, and I want to introduce kind of a new definition. So we're going to say that a pure d-dimensional complex on n vertices is Schelling completable. So this is something we introduced. If there exists a Schelling of delta that can be, taken as the initial sequence of a Schelling of the D skeleton of the n-1 or n-1 dimensional simplex. Okay, so we would like to call this extendably shellable, but that means something different, right? So we call it Schelling completable. So first of all, note that if delta is Schelling completable, then of course any Schelling could be completed, right? So if there exists some Schelling that can be completed to the entire skeleton, then any Schelling can. And also just note that Simon's conjecture is equivalent to saying that any pure shellable complex is Schelling completable, because if you have a shellable complex, right, that is the initial Schelling of some Schelling of the skeleton, and you always want to be able to complete that. And so that motivates kind of our question to say, well, Simon's conjecture says that all pure shellable complexes are Schelling completable. Can we find a subclass, maybe a large subclass that are Schelling completable? And I might kind of mostly skip this slide. I mean, I know there's a couple of shifted fans in the audience, but so if you know what a shifted complex is, I mean, this is, well, okay, here's the definition, right? So a complex is shifted if you can order the vertex set, say 1 through n, so that you have this shifted property, meaning that if you take any face, v1 through vk, you can replace any vi with a smaller vertex, and it's also a face of your complex. And one thing to notice is that if you have a shifted complex, then adding the reverse lexicographically smallest, missing d plus 1 subset is again a shifted complex. And so if you kind of put that together, what that's saying is that shifted complexes are Schelling completable. So I don't know, here's a little example. I hope this is a shifted complex. So this is these are the collection of facets of a 2-dimensional complex. I believe this is shifted. If I take 2, 4, 5, that should be the revlex smallest missing thing. That'll again be shifted. And what I'm trying to get at here is that shifted complexes are kind of an example of something that are easy to see that are Schelling completable. So I want to now introduce another class of complexes maybe people have seen. These will be a bigger class than shellable, but they're called vertex decomposable. Let me first remind you of a couple of definitions. So if you have a simplicial complex and you have a face F, there's this notion of a link and a deletion. So the link is, well, it's defined here. It's a set of faces where they're disjoint from the face, but when I take the union with this face, it is a face of delta. Okay, that's the link. So it's kind of the local information around F. The deletion is what I get when I take away F. So it's the set of faces that are not, do not contain F. And a simplicial complex by definition is vertex decomposable if it's either a simplex or there's this recursive thing that can happen that it contains a vertex V where the deletion and link are both vertex decomposable. And there's also this condition that any facet of the deletion is a facet of the original complex. So it's a bit of a mouthful if you haven't seen this before. I mean, vertex decomposable complexes, I would say at this point are, pretty popular to study. They're often typically a nice case when you're looking at shellable complexes. You often are dealing with a vertex decomposable complex. So yeah, in particular, vertex decomposable complexes are shellable. They were introduced by Provin Valera in the study of the Hirsch conjecture. They were interested in the diameter of certain polytopes and things like that. So last year, I guess as part of an RAU project with a couple of students, Coleman and Geis and Suho Oh, we proved that, well, let me kind of write down the theorem first that says that if you give me a d-dimensional vertex decomposable complex on ground set V, then I can actually order that ground set V with the property that if you take the revlex smallest d plus 1 subset that's missing, call that F, then adding that new face gives you a vertex decomposable complex. Okay, so the punchline here is that there is a way to, in some sort of controllable way, you can actually extend your vertex decomposable complexes to another vertex decomposable complex. And a corollary of that is that vertex decomposable complexes are Schelling completable. So yeah, that was kind of nice. We were able to say, well, Simon's conjecture is about, it says that shellable complexes are Schelling completable. We have this kind of weakening of that. Okay. So remind me, I've got about 7 minutes. Is that right? I don't know who's in charge of time here, but I think. Interrupt me if I'm wrong about that. So I'm okay. Okay. So a couple of applications. I don't know how much I want to say, so I might have to skip some slides here. But so what's an example of a vertex decomposable complex? We saw that there's these shifted complexes. There's also something called a matroid, which again, many people probably know about. Let me just remind you of the definition if you haven't seen it before. I'm going to take this perspective that a matroid is a certain kind of simplicial complex. So it should satisfy an exchange property for the bases, or what we'll call the facets here. If you have any two facets of the simplicial complex, then for any element that's in, F not G, then there's an element of Y, element Y in G, but not F, where I can exchange the two. I can take away X from F, throw in Y, and that should be a facet of this should be delta, right? Okay, so again, this is sometimes called the independence complex of the matroid. So matroids are vertex decomposable. They also, of course, these are well-studied objects. They have many characterizations as well. One very nice characterization, especially for us, is they can be characterized by the property that if you give me any ordering of the ground set, then just putting those facets in lexicographical order is a Schelling. That actually characterizes. So that's a property of a matroid, and it's characterizes them. And so what we were able to do is to say, well, can we kind of play around with this kind of property, knowing that these guys are Schelling completable? So our proposition here says that if you give me a rank D matroid, and you give me any ordering of its ground set, where we know that the smallest guy is in there, right? So, my matroid is a collection of D subsets. I want to put an ordering on the elements in the ground set with the property that the smallest, the lex first guy is in there. Then it turns out that if you take the rev lex smallest, the subset that's missing, that'll always be vertex decomposable. So it kind of tells you, this is kind of like telling you, how can I get to a vertex decomposable complex? Sort of how much flexibility do I have? And this tells you that there is a good amount, that if you just give me any ordering with this condition that I have the smallest element as a facet, then the next small rev lex smallest thing will be there. We'll give you a vertex decomposable complex. Let's see. I think I might skip this this slide for now. But another thing that we were able to prove here is that we go back to these complexes with few vertices, and we already saw that shellable and extendedly shellable are the same when you have a D-dimensional complex on D plus 3 vertices. And it turns out that the same thing happens for vertex decomposable. So if you have a shellable complex D-dimensional on D plus 3 vertices, it's actually vertex decomposable. As far as we could tell, this was not in the literature. Maybe it's out there somewhere, I don't know. Maybe people in the audience have seen this before, but what this says is that the shellable, extendably shellable, Schelling completable, and vertex decomposable are all equivalent in this context. And again, this is tight in the sense that you have complexes that are 2-dimensional on 6 vertices that are shellable but not vertex decomposable. Okay, so maybe just a couple of further thought. I guess I have 3 slides of further thoughts here, but so kind of, looking forward to kind of what we're thinking about now. So just, we briefly touched on this idea of what a chordal clutter might be. We call them quotient chordal clutters. I just want to point out that there are many people actually who think about chordal complexes from different perspectives. You can think about what a chordless cycle means, and you get some notion of a chordal complex. You could also take the definition of a simplicial vertex. You get another, independent notion of a chordal complex. And most recently, there was this team, Bigdelipour and Zard Nahandi. They have this nice construction of what they call chordal clutters, involving what are called simplicial ridges. So I'm not going to go into the definition, but we had actually conjectured in our paper that that these quotient chordal complexes that I talked about were actually chordal in this sense. But recently last year, Benedetti and Bolognini, they proved that actually they are not chordal. So then there exists, well, I should say not chordal in general, right? Of course, sometimes they are, but they're not always. There exist complexes that are quotient chordal, but not chordal in this sense. So anyway, that's kind of a recent development. One other thing I want to point out is that this perspective of taking exposed edges and exposed circuits gives you a new way to think about Simon's conjecture. And it turns out that if you parse everything, Simon's conjecture is equivalent to the following statement, that if you have a quotient chordal complex, which was obtained by removing these exposed circuits, then it itself should admit an exposed circuit. That's equivalent to Simon's. So let me just maybe focus on this last bullet point here that says that what this is saying is that if you want to find a counterexample to Simon's conjecture, it amounts to finding a collapsing of a simplex with certain conditions that gets stuck. And so, that is actually kind of an industry. People think about kind of collapsing simplices in ways that, well, get stuck, or, what are the obstructions to collapsing? And so this is kind of something we're thinking about now. My last slide is, again, let me just remind you that well, Simon's conjecture says that all shellable complexes are Schelling completable. We prove that vertex decomposable complexes are Schelling completable. It turns out there's a family of complexes in between. They're called K-vertex decomposable. So they interpolate between the vertex decomposable, which is the K equals 0 case, and shellable, which would be the K equals D case, where D is your dimension. It turns out you define these things by just, restricting the dimension of the shedding face. If you remember the definition of vertex decomposable. I just gave you an example here that if you take this complex, two-dimensional complex with those facets, you can check that it's not vertex decomposable, but it is one vertex decomposable. I have a typo here. I guess I was going to tell you what the shedding face is. I don't know what it is right now, but yeah, so I forgot to tell you what the shedding face is. Is it like 1, 2 maybe? Anyway, so the last question I want to ask is it true that one vertex decomposable complexes are Schelling completable? That's kind of actually the project for this summer's REU. We're gonna look at that question. That would be like the next step of the family of complexes that might satisfy this kind of Simon's type conjecture. So, okay, so there's my last attempt at some Spanish there. So thanks for the attention. Thanks for listening.
Any question? ¿Alguna pregunta?
Yes, I've got a question. Anton,
Sure.
you mentioned shifted complexes and matroid complexes had this nice property that you can put an order on them, and the next revlex face you can always put in. I think I got that right. So you know that Jose Samper has these quasi-matroidal complexes that are sort of somewhere between shifted and matroid. Is this property true for those complexes?
It's a good question. Yeah, I mean, of course I know Jose, and I know he's working on these things. That's a good question. I haven't thought about that. You could probably answer it better than me. I can't remember his definition offhand, but
not precisely, but it is somewhere between, well, somewhere between shifted and matroid.
It includes both. Is that right?
Yes, they're both special, or if not exactly shifted, something very close to shifted, but basically, yeah, includes them both as special cases.
That's a good question. I'll put that on the list for the REU for sure. Thanks.
Great.
Any other question? ¿Alguna otra pregunta? Ok, pues muchas gracias, Anton.
De nada.
Okay.
Let me stop sharing.
Yes, thank you. Nos pidieron la cuenta para 10 minutos antes de la plenaria. Yo pienso que es mejor que la última plática la pasemos mañana a las 7:25, 9:25 del centro. Y bueno, mañana a las 12 los invito a todos para prender la cámara para tomar una foto de todos a las 2 del centro. Tomorrow at 12 o'clock of Hermosillo, 2 afternoon in the center of the country. We are taking a picture and of the workshop, and I invite you for the photo. Inclusive the assistants, we will permit to turn on the camera. Then tomorrow is all. The last talk is we are changing to tomorrow at 7:25. See you, everybody. Thank you very much.
See you tomorrow, guys.
Okay. See you tomorrow.